Hello and welcome to this Oasys webinar on concrete design. Led through it by myself, Peter Debney, application specialist. Now we have three programs in the Oasys suite which look at concrete design: ADC, AddSEC, and GSA building. Each look at different aspects, each have a different approach, and which you go for will depend very much on your particular case. Now we'll start at the easiest end with ADC. Now ADC is concrete element design program. Does beams, multi-span beams and slabs and columns, and it's simple in that you give the dimensions and the loads, and ADC will work out the reinforcement for you. Because it's all simple, it's quite restricted on section sizes that you can work with, because everything has to be automated. And if you want to do anything out of the ordinary, then you have to look at something like AddSEC. But ADC works to a number of international codes, including the Euro codes with national annexes, but also Hong Kong, Australia, America, and Indian codes. There's not too much to say about ADC. Let's look at it in action instead. So what I'm going to do first of all, I'm going to create a multi-span beam. I'm going to change my design code, GB, Eurocode GB. I'm going for beam design, and I'm going to ask for 4 spans. Now, everything in ADC is changeable after you create the basic beam model, apart from this number of spans. That's fixed, I'm afraid. Also, I won't go into the rib slab and solid slab. They're very similar in principle to the beam design, of the important differences. So if you know the beam design, then the slab design will be quite straightforward. So first of all, number of spans, span length. So let's go for 6-meter spans, and the section size. Well, we've got a choice of sections: rectangular T, taper I's, taper T's. Let's go for a taper T section, I think. And let's see, 500D, meter flange width, flange thickness or slab thickness, say 250 slab. And the web of the T section, top and bottom, say 400, tapering down to 300. Supports. I think the left-hand end will have a cantilever support, and we can have column support at the other end. And speaking of columns, let's put in column supports. And so we need to give section size to the column. Let's say a circular. Go 400 diameter. Thought it would be 4,000 then. So 400 diameter column, 3 meters long. So you pinned at the far end. Copy that to the other layer. Other options, specifications. Whether you want to add in our own user, because ADC will do patch loading on the beams. Lateral stability, that will design deep beam checks or not, so on. Materials, what concrete materials we're using, what reinforcement materials we're using. I'll take those defaults. Loadings, well, if I stick, let's say 10 kilonewtons a meter run dead load, maybe 6 kilonewtons meter run live load. Self-weighted concrete redistribution, we can add this in now or leave it for a moment. Cover, you can type in the values of cover, but there is a cover code option, and you pick an appropriate exposure class. It then updates the cover to suit. Sizes and limits. Now ADC needs to know what bar size to work with. We have default sizes, and we can also add our own bar sizes appropriately. We then need to tell AddSEC what bar size it can use where. So those link sizes and some all look good. Spacing is all about constructability, poker access and that sort of thing. And selection criteria, this varies between section and section. I mean, obviously we've got taper beam, so we've got trapezoidal links as an option, but those can be rectangular and so on. So that's good. Let's fire up the model, and this is our overall section. Now at the moment we've got a 6 meter cantilever at the end, which is not good, so let's reduce that down to just 2 meters. And the supports, I think, at the far end. Yeah. Just put a pin support at the far end. Now we also have our loads, dead and alive, and we can analyze this nice and quick. So we get our bending moments and shear forces on the beams. And let's go to design. And what design do will basically choose a reinforcement for us. No warnings, always good. Now let's look in detail this. So longitudinal bars, links. You can see the bars. And if we click on the span, you then focus on that span and also adjust these top views as well. Very quick, very straightforward. Similarly, we have column design, very popular amongst the piling designers. And the thing about good about column design in AddSEC is it automatically adds in additional moments for you, so you can't forget those. And I'll do a 450 pile. Again, column grades, effective lengths. Now these effective lengths, well, if it's a pile, let's say it's going to be 3 meters. Okay, there you can go and set these options in more detail. Axial loads. Let me see. Let's. Oops. 3,000 kilonewton load onto this. Now, I could put moments in here. I'll leave these off because then you see the moments created. Created directly by the axial load. Size limits the same as before. Slightly different. Reduced choices. Arrangements. Now this is columns. Now circular columns. You either get a ring with a number of bar options, possibly multiple rings, possibly diameter. If it was square, to have a choice of bar arrangements. Cover, let's go for 75 cover. And checks, again, detailing rules, which you can either have active or switch off as appropriate. Now it's told me there are 72 possible sections. What AddSEC will do is go through each of these and check them for detailing rules and only give me those which pass those detailing rules. Those doesn't. we have, well, at 72, we have about 24 sections. With various bar sizes and choices. Okay, we can now go straight for a design, and it says 7 of those have failed. Let's look at these in detail. So output view, I'll include the invalid sections. So we then see all the various designs, and you see reasons for various sections why they failed, sections which have passed, and we see at the bottom what's the most important part. You see the section in red are columns which have failed, columns in black are sections which have passed, and columns in blue, or there'll be one line in blue, which has the minimum area of steel. And we can see this is working at about 83% utilization, section 58, which is this one. And when we had just axial loads, you can see that it's added on the eccentric moments onto that to make sure they don't get forgotten. Apart from overall design, you can also ask for the axial moment charts. And you can see the point load in there, and also moment charts. Not quite so important for a circular part, but now these charts are produced by AddSEC. You don't need AddSEC to create these charts, but you will need AddSEC if you want to get into more detail and so on. Now, AddSEC is our nonlinear cross-section analysis program. Unlike ADC, which only does very simple programs, very simple sections, circular or square for columns, and a reduced number of sections for beams, AddSEC will allow you to create anything and analyze it. Whether it's reinforced concrete, composite sections, composite columns, FRP materials, carbon fiber wraps, GRP rebar, that sort of thing. It also allows you to do sections from the simplest to the most complex, including pre-stressing on the bars and so on. Outputs, these axial moment charts that we saw just now, moment charts, also moment axial stiffness charts. So you can get the EI value of the section over a range of axial loads and moments, which you can then feed into your finite analysis such as GSA. If you give it loads to work to, it will tell you how much a section cracks, including Eurocode cracking, which is a difficult thing to do manually. And again, like ADC, it's a wide range of international codes, slightly more than ADC. ADC will catch up shortly. So let's look at AddSEC. What I'm going to do is again create a Eurocode. Let's go create a square column this time. Obviously, lots of the dialogues are very similar because we use shared dialogues between the programs. But you see, with AddSEC, you've got a much larger range of sections to choose from. Let's go for the rectangular for the moment, and we'll add a 600 by 400 section. And I'll give it the reinforcement size for bar spacings and so on. And I'll go for a template reinforcement. And notice we put in beam rearrangement, a column arrangement. If this is going to be a column, I'll make a column. Cover code as before. Links, Now these links are there to position the main bars, not AddSEC can't do shear design because it is a cross-section analysis, and shear is more three-dimensional and requires knowledge about supports and so on. So how many bars? 8 bars, one each corner, one each face. That will do, I think. And we'll put in 20mm bars. And there is our arrangement. Now we can also add in additional bars to there. Let's put in a huge bar dead center, for example, and deal with the effects of that. I'll leave it out for the time being. So there's our section. Like ADC, we can run axial moment charts to quickly view the section capacity. Likewise, moment charts. Let's say 0 to 4,000 step 1,000. This will create 5 loading cases on the section and give us the various moments capacities for those axial loads. In some respects, it's another view on this stress bob, looking in plan rather than elevation. And taking slices through it. Let's talk about producing a 3D view of this, because we shall see that quite interesting when we come to it. Okay, and you can also simply do the moment stiffness chart. And again, I'll go 0 to 4,000 step 1,000. Whether short-term or long-term loads. Just calculate that. And there we go. So and we can see the varying axial loads where the concrete cracks up until final failure point. Now these values, you can copy these out into Excel or whatever, or get the results in the tablet, in the text output and so on, and take these into GSA for more accurate deflection calculations. Meanwhile, so that's basic loading, but we can also actually put in actual loads. So I put in my dead and live loads. Well, these are just the low case titles to begin with, and then the loading we put in. Let's say low case 1. It's going to be a section force, and I'm going to say 1,150 there, and low case 2 is our variable loads. I'll say the same again, actually, for simplicity. Now, these loads can then be combined into ultimate state cases. So 1.35 L1 plus 1.5 L2, dead and live, or serviceability limit state cases. Let's just check our serviceability for the individual load cases. So serviceability, this will give us the various results, including the moments on the section, the strain planes, which at the point where the section is balancing the applied loads, and the crack widths at the bottom. And you can see the crack widths are nice and small. Now, which sections? We can see the two locations and which bars are the ones driving the cracking in this case. Alternatively, we can check for the ultimate limit state. And it's saying that our moment is greater than the strength. Let me just check that. Put too much moment on. Yeah, okay, I'll just rerun that with a lower moment. That's better. And we then see the stresses and strains in the concrete under those applied loads, or if we do US strength, subtly different, but this time it actually works out the moment capacity for that applied axial load, and then the stresses and strains given here are then at the ultimate limit rather than just the applied loads. Now we can do simple sections in AddSEC, and we can do more complex ones as well. Let me add in a new section into this file, and this time I'm going to add a perimeter. Now, perimeter, you can actually define the outlines, and we can use pre-supplied sections. You can type in the values yourself, or we can add in now. This is a core wall manipulator case. Now, I could add lines of reinforcement in there, but what I'll do instead is I will use the tool up here, and likewise you can import bars from CAD. I will add perimeter bars onto this section. Let's say 30mm cover, horizontal laces on the outside, 2mm bars, 2 feet sensors. It then goes around the perimeter and adds in all the bars for you. And then again, you can then do the capacity checks as before. Now, I mentioned about taking stiffness values into GSA. GSA is our finite element analysis program. Now, within Arup, it's just one version. Outside Arup, we sell GSA in 4 different versions. GSA analysis is sort of the base value, base case, which is the only one which doesn't have the concrete design in. But we have one for bridge engineers. We have one for building engineers. Basically, they add in steel concrete design and footfall analysis. Building includes soil structure interaction. Bridges includes bridge loading. And then we have the suite, which is absolutely everything. Now, this is the same as the internal Arup version. And these all have, after analysis, the RC slab design option, which enables you to take all the applied loads, out of plane moments, in plane forces, and design reinforcement on those 2D elements for that. And again, you can see the range of international design codes that it will work to. So let me do that now. To save time on the modeling part, I've created the model here. Now, one of the things you'll find with concrete design is that it's a flat slab, and therefore you tend to get very high peak moments at the columns. There are a couple of ways of dealing with this. You can let me switch the oops. You can add in thicker elements at the connection points, or you can add in constraints, and I do have some constraints set up in here. What I'll do is I'll not PA2. Now what this will do, if I switch on my display of rigid constraints, look at the stages, you see with constraints I have rigid constraints and an opening at the other stage. I have no rigid constraints and the thicker elements in the middle. Now if we just do a analyze all for our applied loads, this will run the basic model, and this basic model, as I mentioned, has loads already applied, but interesting enough, it has edge loads. Now edge loads are a bit tricky in their fee analysis because you've got to specify line, and what I've got there is a line of bar elements around the edge. What these bar elements will do is you purely pick up the UDL. They have absolute minimum cross section, so no real self weight, no real stiffness, but they will shed the load into the slab. So analyze that. What we then get is deflections, and deflections showing the bars. Let me just switch the deformation of the bars off. Actually, let me switch off the undeformed shape so it'll be easy to see. We can see our deformed shape, and let's contour that. So see our deformation, but we also want the moments on here. Now I've set up a combination case already. These combination cases are much easier if you use the factors tab. So let's look at ULS condition, and rather than displacement this time, we can get maximum moments. See peak values in the middle, the projected moments. Now what I'm going to do, I'm going to switch off the central elements. Let's rescale so we can see these a little better. And you see we do get a little bit slight anomalous values around the perimeter, but they're not too bad. So moment in the X direction. Now this moment MX basically gives you reinforcement in the X direction, and Y moment in the Y direction, torsion on the elements and the combinations thereof. Now you could design this direct by hand, but hey, we've got the ability in here already. So what we're going to do is set up design specification, which we can set to whichever code we like, Eurocode in this condition, and then under my properties, design properties, I've set up a property here, property 1, which is the design property for, not sections, 2D elements. Note, row 1 gives design properties for row 1 and 2D elements. I haven't got a row 2 because I'm not interested in the column connection design, because that's all within the column. Now the slab properties, we have the concrete grade, the reinforcement grade, the direction of the reinforcement related to the local axis of the elements, which so it's currently set to the global axis, which means X will be in this direction, Y will be up the screen. Won't be calculating the bars required. It creates the area of bars required, which means you need to specify the surface to centroid of the reinforcement for each layer. I've got minimum areas of steel. Let's reset these back to 0 for the moment, whether compression or tension. What we can now do is, on the contouring, ask for the reinforcements. Now, when we do this, it goes away and designs the reinforcement, but also change the contours to pick up standard spacings. I will also change the units here because there's a slight glitch in the current version that's showing the wrong units here in the table. The number's still correct. It's showing the wrong centimeters rather than millimeters. We're getting some quite high values in the middle, but let's look at the other directions. The B direction, bottom A, and the bottom B. Now we can edit these contours to suit, but I do happen to have some saved views already set up, which have reduced display on the reinforcement, and also option there to show where reinforcement will be hitting the maximum level and so on. So you can customize these to suit your requirements. Now, the reinforcement at the moment is based directly on the actual thickness of the slab. What we can do is we can override this value. At the moment it's set to 325, which is working quite well. Put it in the middle, but we can change this to say, let's say, put in a 250 slab, and these other views will then update, and we can quickly experiment with different section sizes, slab thicknesses, and we can see 250 slab. I'm beginning to get overloading of reinforcement in the middle. Let's say 275. And you can keep adjusting this until you get to a section size that you like. Now note the black areas. If I just reduce these displays down. If I set that back to say 250, okay, 200. Let's really push it over the edge. There we go. we're getting some black areas in the contours. These black areas show where the concrete is crushed. I'm also getting some white areas, which shows perhaps we're getting contours beyond the limits set at the moment. Let me rescale those. Just adjust the contours so we can see we're getting some quite large amounts of compression reinforcement. But basically, the most important thing to note is the black ones, black areas, concrete crushing. Can't create a can't find the right reinforcement in there. Obviously, once you come up with a section slab thickness you like, then delete results, update the section properties, reanalyze the final self weight, and so on. Excellent. Well, that's a very quick introduction to the various concrete design capabilities in the 3 structural programs. Is there anywhere else you'd like to look in more detail at concrete design? So if you have any questions, do please type them into the questions box and I'll see about answering them. Okay, got a question. How can we do pre-stressed concrete? Pre-stressed concrete, can't do it in ADC, you can do it in AddSEC. AddSEC, let me just let's quickly do let's say a circular pile with some template reinforcement. So we've got general reinforcement, template reinforcement. We can also add in pre-stress bar, let's say 20mm bar, straight down the middle, and I can pre-stress this under load, and I can also then say whether the forces that we're applying for the lesson cases and everything will include the anchorage effect. So does this preload need to generate additional moments and axial loads on this section, or are they already in there? In this case, I'm saying apply those excludes, so AddSEC will add in the pre-stress effects from tension on that bar. We can also display by that pre-stress, so you can see which bars are pre-stress and which are not, and obviously these other analyses will then take that pre-stressing into account. Question about, does ADC do shear design for circular sections? Now ADC does do shear design for the beams, but it doesn't do the shear design for the columns at this precise moment, whether square or rectangular or circular. It's something we're looking at, but it's not in there at the moment. Watch this space. Okay. Can we import a bending shear envelope diagram into ADC for it to do rebar design? You can't do that at the moment. We will be introducing reinforced member design into GSA some point in the near future, but not in the ADC at the moment. You'd have to generate the loads. You have to add in the loads, possibly the user-defined load cases, to get those moments. Alternatively, if you know the moments and you've got a good idea of the reinforcements, you can put those moments directly into AddSEC and and check your designs there. So a question coming in pieces. When you overwrite slab thickness in 2D elements, does it take into account slab self-weight? When you do when you override the thickness here, no, this is, you're changing the design without changing the analysis. Once you're happy with a section, let's say 300, and then gives you results you like, what you then need to do is erase these results, go into the 2D properties, change that to 300, and then rerun the analysis. Now that will take the self-weight into account automatically, but you have to do the reanalysis. With ADC and so on, you change the depth, then everything is updated to account for that, for the new section. Okay. Oh, actually, while I'm here, let me just adjust this, because we talked about minimum areas reinforcement. I took these off. Let me put these back on, which was 3.9. Ooh. And we'll see then the graph, the charts are then giving us the minimum area steel plus then the patches where the you need additional. You can see these brown areas here. This is compression reinforcement steel, even with the 300 slab. Only in small patches. Something to watch out for in that central strip. Okay, that's like all the questions. Say thank you for attending. I hope you found that useful. There is a closeout survey if you've got any additional questions and want more feedback and so on when this webinar closes. Thank you all for attending, and I look forward to seeing you next time.